It says we're recording. Ooh, oh my God, everything falling on me. Hi guys. I miss you already. We'll get through this though, right? For sure. All right, I hope you're all doing well. I'm sorry I couldn't do, the first lesson for this. It just, with 4 classes of me recording and all of these kinks and everything, I had, whatever, it is what it is, but I'm here. Yay. So if I run into those kinds of things again, you might see Mrs. Fox's videos again. Hopefully not. Hopefully I get ahead of things and I'm not behind and you see me instead. Okay. But either way, you're golden. Yes? All right. So you learned, well, shouldn't have been any new information yesterday, right? It was all vectors that you've learned before in pre-calc for sure, algebra 2 trig for sure, a little bit in advanced math trig if you came that way, and then we've done some this year also. So kind of just a throwback and doing some more with vectors. Yes, vectors in the plane. So, and especially if you've had physics, hopefully everything's connecting now. Right? Okay, so we're still in the same section, still with vectors. We're going to just continue to do a few more things. So first example 4 says a Boeing 727 airplane. It's flying due east, that's the positive x-axis, at 500 miles per hour in still air. And it encounters a 70 mile per hour tailwind acting in the direction of 60 degrees north of east. The airplane holds its compass heading due east, but because of the wind, it acquires a new ground speed, right? So if you've ever flown to Hawaii, they're going one way with the wind and with the wind currents and coming back against the currents. If you've ever paid attention to how long the flight time is, one way is, it's like almost an hour difference. I want to say like it's a 45-minute difference between going there and coming back. And it all has to do with the wind, right? And so, and that's true not just to Hawaii, to anywhere, right? Whenever when they come up with the winds, come against the winds. And so the pilot will set its direction in a certain area, but if the wind starts pushing them in a different direction, then if we're from the ground, that perspective, the velocity is changing, the speed changes, the direction is changing, all of that. So he's got to adjust, right? So let's draw this out. Okay, so we've got that the airplane is flying due east, so that's the positive x direction. Miles per hour is its speed, and so I'm going to let you be the, let me get a laser pointer here. Whoop. Okay, so I'm letting you be the vector of like the direction that he's heading, right? And he's flying 500 miles an hour, so the speed is 500, which is the absolute value or magnitude of that vector. And then the wind has a magnitude of 70 since its speed is 70. And so I start by drawing vector u going due east, so directly positive. Why is it putting a little v on top? Now it's weird. Okay. Directly due east with a length of 500. And then I'm going to draw vector v. It says it's going 60 degrees north of east, which means that this angle here, so here's east, north of east means up here. So it would be the normal trig, 60-degree angle. Right there, north of east. Here's east. North is this way, so east. North of east would be this way. If it had been south of east, you would have drawn it going down this way. All right, so you got a 60-degree angle in between them, and the length of it is 70. You want to try to kind of be proportional. It helps with your drawings. All right, so I'm going to use the parallelogram rule, which we went over yesterday. And so I finished off the parallelogram, and then u plus v would be this length, this vector going to the diagonal. And so we can just add them component-wise in order to add them. Come on. And so that's 500 cosine of 0, sine of 0. So the angle is 0 for u with a magnitude of 500. That's u's component. And then v, if I do the components for v, it would be a length of 70. The magnitude is 70, but the angle is 60 degrees. So 70 cosine of 60 degrees is your x component. 70 times sine of 60 degrees is your y component. I'm going to add these two vectors together. If you remember, this first guy would be 500, 0. This guy would be 70 times 1/2, which gives me the 35. This is 70 times rad 3 over 2, which is 35 rad 3. I'm going to add the two together. 500 plus 35 will give me 535. 0 plus 35 rad 3 will give you the 35 rad 3. So this, like, what is the x and y displacement for this vector? It would be 535 in the x direction, 35 times rad 3 in the y direction to get to this point right there for u plus v. All right, so that's its position of where this is right there. And then what we want is the magnitude. And if I go too fast, then just pause and rewind. Hopefully I'm not going too fast for you. But I also don't want to make this video an hour long either. All right, so we want the magnitude to figure out that's the length of this vector. And you use Pythagorean theorem, right? Square root of the x component squared plus the y component squared. And you put that in your calculator, and I end up getting 538.424 miles per hour. So the wind is actually pushing them faster. Isn't that nice? All right. So that is, we want that. That's the new ground speed. Ground speed. So ground speed is this. This is the ground velocity vector, and then the speed would be that. So that's your new ground speed. To get the direction, I want, what is this angle right in there? Yeah, and so tangent of theta is equal to y over x. So I took the y component, 35 rad 3, divided by the x component of 535. And when you put that in your calculator in degree mode, you're going to get 6.465, going to 3 decimal places. And that would be north of east. So here's east, north of east. It's going to be that guy right there. All right. Oops, let me go back. Okay, so that is your ground speed and the direction. So velocity, if you remember from previous chapters, is the first derivative. So dx dt, first derivative, and the acceleration is the second derivative of, so second derivative of x with respect to t. This is if they're giving you x in terms of t, right? So that's why it's not dy dx, because most of the time with velocity and acceleration, they'll give you your in terms of time, right? So that's why it's your independent variable is t for time. So when moving in a plane, if we use vectors, we simply treat the components as separate linear models. Treat them as separate linear models. So let's look at this example 5 that says a particle moves in the plane so that its position at any time t greater than or equal to 0 is given by sine of t comma t squared over 2. So that's its position at any time greater than 0. They want us to find the position vector. So writing these with parentheses means it's just that point, right? So you can generate a bunch of points when t equals 0 and 0.2 and 0.5 and 0.1, and you'll have like a bunch of dots, right? To find the position vector, that takes wherever your position is, it takes a vector going from the origin and drawing an arrow pointing to that point. So all we do is take this position point right here and we turn it into a vector by using angle brackets. So if they're asking you for a vector, right, then you should have angle brackets. It's the vector. This is the point. This is the vector. But it's the same, same guy. Just, if one is a point, then one is a vector. Yeah. All right, so that's the position vector. The next thing they want to know is find the velocity vector. Well, velocity is just the first derivative. And so we'll take the first derivative, of sine, which would be cosine of t, and taking the derivative of squared divided by 2, pop that 2 in front, and drop the exponent by 1, so the 2's end up canceling. Your exponent is now a 1. So your velocity vector is cosine t comma t. So this is for any time t. If we were to draw out the position graph of where this is going, the points would be generated by this. You could drive vectors to each of those points. This is going to give the velocity, which will give you the direction of motion. Remember, when velocity is positive, well, when it's in an x plane, right, when you're just moving horizontal, velocity is positive, you're moving right. When velocity is negative, you're moving left. I don't know if I'm mirroring you, if I'm mirrored or not, so I'm probably pointing the wrong way, whatever. Here, we're actually moving in the plane, so you're moving like, if it's a positive x and a positive y, then from that point, it's giving you your slope, right? You're moving x and y, and then there's your new point. So velocity is going to give you that slope, right, of the change to get to the next point. Yeah. If it was a negative x and then a positive y, from that point you would go left and then up, and so on and so on. Acceleration vector is going to be the second derivative. And so you take the derivative of cosine, which is negative sine. The derivative of t would just be 1. So there's your acceleration vector. Not that you need to know this yet, but like next year, if you continue on with me and go to multivariable calculus, you learn that acceleration will actually give you, like, let's say it's a curve, the position, curve, right, is like curved. The acceleration will tell you like which way it's curving. It'll always point into the curve. Don't need to know that yet, but just an interesting tidbit. When they tell you to describe the position and motion of the particle at t equals 6, your position would just be plugging in a t, and your position will be plugging 6 into t, sine of 6, and then 6 squared, here's your position, 6 squared divided by 2 would be 36 divided by 2, so I get 18. Sine of 6, I wrote it somewhere, is like a negative 0.279. So your position, like from the origin, would be a little negative x and then a 18, so a positive y. The velocity, you would just plug a 6 into the velocity vector, is cosine of 6 comma 6. Cosine of 6 is about 0.96 and then comma 6. So from that point, you're moving a positive right direction and then an up direction, right? So you're just continuing moving in a positive direction there. But because it's cosine, we'll end up, coming around and going negative also. So this will curve, do a bunch of stuff, but, and then acceleration is just plugging in 6 into t here, so you get a negative sine of 6 comma 1. And so at t equals 6, you're moving right and up, right? But that'll change depending on t, right? When you get into 6 is a positive cosine, right? It's right before you come back to the positive x-axis. So anyway, but as soon as you get into quadrant 2 of values that you're taking cosine of a quadrant 2 or quadrant 3 angle, all right, then you're in the negative value. So, all right, so that's that guy. Suppose that a particle moves along a smooth curve in the plane so that its position at any time t is given by x and y, where x and y are the differentiable functions of t. The particle's position vector will just be taking that point and turning it into angle brackets. And your book uses r to represent the position vector. So it'll be x, and x will be some function of t. Y will also be some function of t. The particle's velocity vector is given by taking the derivative of x with respect to t and taking the derivative of y with respect to t. And velocity will be a vector. angle brackets. The speed, remember velocity vector. A vector will give you magnitude and direction. So that's why a vector has these angle brackets. It'll tell us which direction we're going in the x and which direction we're going in the y. But the speed is, it's a scalar is what we call it. It's not a vector anymore. It's the magnitude of your vector. Some books do 2 lines here for the absolute value. Our book must use just a single, like looking absolute value, but you're talking about the magnitude. Remember, speed is a scalar, definitely not a vector. It'll be an actual, like, I'm going 538 miles per hour. Hopefully you're in a plane and not a car. There's probably not even any cars that go 500 miles an hour, so that's stupid, but whatever. Okay, maybe they do. I don't know. All right. The particle's acceleration vector would be the second derivative of your position, or the derivative of velocity, but again, of x with respect to t, and then of y with respect to t. And then the particle's direction of motion is the direction vector, and we can get that from direction of motion is your velocity vector divided by its magnitude, so that you'll just get a unit vector and then pointing in that direction. The velocity is going to tell you which direction it's going, but when we divide it by its magnitude, then it gives us just a unit length. It's pointing in the same direction, but at length 1. All right, so that's the first equation. And now we'll do an example of catching a fly ball. As a baseball leaves a batter's bat at an angle of 60 degrees from the horizontal, 60 degrees, so that's nice, it's working like trig, traveling at 110 feet per second, a fielder who's standing in the direct line of the hit with his glove at a vertical reach of 8 feet, so he can reach as far as 8 feet, catches the ball for an out. His feet don't leave the ground, so that's his feet are still on the ground, reaching all the way up, he can reach 8 feet. We want to find the position vector of the baseball in time t in seconds. So position vector, we're saying the ball leaves the batter's bat at an angle of 60 degrees from the horizontal, traveling at 110 feet per second. That's giving me the length of that vector. So my x, oh yeah, by the way, we're on Earth. We have gravity. So the gravity is going to affect the y direction, like the y component of that baseball, right? If you were in a vacuum, we would just do x equals magnitude times cosine of your angle, and then y equals the magnitude times the sine of your angle, but that's like in a vacuum. Here on Earth, we have gravity that affects us, and if you've taken any physics, these numbers will look familiar to you. If you haven't, then you're just going to remember them. No big deal. All right, so position vector. So we're going to write it as a vector. First, find the x component. That's just magnitude, 110, times t, because it depends on your time, right? And then cosine of 60 degrees, which will give you, cosine of 60 is 1/2, so you end up 55t. Will tell you at each time, because it's traveling at 110 feet per second, so I wrote 110 here, but that's not exactly true. It's in one, I guess this would be at 1 second. Here's what the velocity vector looks like, right? At 1 second, the length is 110, but it changes. At 2 seconds, it'll keep on going, right? So this will give you your horizontal component. Your y component, we've got this gravity involved, right? The gravity is pulling it down. And if you remember any projectile, that's the reason why. When you throw a ball, kick a football, what else do you get? Whatever. Any ball thrown in the air or hit in the air, what goes up must come down on Earth, right? And so that's why it ends up taking on a parabola shape. I was going to say parabolic, but same thing. A parabola shape, right? So you'll do 110 times t times sine of 60 degrees, but then you're going to subtract from gravity, you're going to subtract 16t squared. Like I said, if you've done any physics, that should look familiar to you. If you have not, you're just going to memorize the fact that gravity is minus 16t squared. All right, so sine of 60 degrees is rad 3 over 2 times the 110 gives me the 55 rad 3 times t, and then minus 16t squared. Putting those together, your position vector is given by 55t, comma 55 rad 3t minus 16t squared. So there's your position vector, right? And then we want to find the velocity vector. So velocity vector, you're just going to take the derivative of that position vector. The position vector was 55t, so derivative would be 55. And then the position was the 55 rad 3 times t, and then minus 16t squared. So taking the derivative of both of those gives you 55 rad 3 minus 32t. And then what time t does the fielder catch the ball? And also, how far is he from home plate? So when does he catch the ball? Well, he catches the ball at that vertical height of 8 feet, right? But we want t when your y is 8, right? So we're going to set the y component of your position, right? 55 rad 3t minus 16t squared was the position of your y component. And then we want to set that equal to at 8 feet. When is the vertical component equal to 8 feet? Yeah, feet. Okay. So you set it equal to 8. Subtract, or I'm going to add the 16t squared over. I'm subtracting the 55 rad 3t, and then you got plus 8, setting it equal to 0. You can do quadratic formula. We're going to use the quad form in our calculator, right, where you'll put a is 16, b is negative 55 rad 3, and then c is 8, right? Put it in quad form, and you should end up with your calculator giving you that t is 5.869 seconds. Go into 3 decimal places because AP Calc exam, they're going to have you go to 3 decimal places. See, we're normal. I'm drinking coffee, right? It's period 2. Okay. Then they also want to know, how far is he from home plate? All right, so from home plate, that's the x component. That's the horizontal. Think about it like you're walking horizontal, and your vertical is the y, horizontal is the x, or on flat ground is the x component, right? So we want the x component when t is 5.869 because we just found it. And so your x component was 55 times t, so you just go 55 times 5.869, and you'll get 322.795 feet. All right, we got one last part, and that is to figure out how fast is the ball traveling when he catches the ball. How fast is it traveling when he catches the ball? So that's the speed of the ball, which is the magnitude of the velocity. And when he catches the ball, remember we just figured out that it's when t is 5.869. So we plug it in. Your velocity was 55 for the x component, but then 55 rad 3 minus 32t. So I'm plugging the 5.869 into the t. Magnitude is, we're doing Pythagorean theorem, right? X squared plus the y squared. And then you put it in, and you're going to get 107.655 feet per second. Yeah. Now, more likely than not, right, they will probably give you an answer instead, and I think your homework does this to you. If they say, find how fast it's traveling in miles per hour, but yet they gave you everything in feet per second. That's what we call dimensional analysis. And if you're interested in engineering at all, you're for sure going to be doing tons of this. All right, so to convert it to miles per hour, we start with 107.655 feet per second. So I'm going to write feet on top, second on the bottom. And then I want to convert to miles. I want to convert feet to miles, and I want to convert seconds to hours. So I'm going to start with converting the feet to miles. There is 5,280 feet in 1 mile. Should you know that? Yes, you should. We don't give it to you. So now feet cancel. So now I've got miles per second, and now we just want to convert seconds to hours. So I'll go. I know that there are, you could do it in 2 steps if you wanted to. There's 60 seconds in a minute and 60 seconds in a minute, 60 minutes in an hour, which makes it 3,600 seconds in 1 hour. But you could do those as 2 fractions if you wanted to. All right, so you're going to go 107.655 times 3,600 and then divided by 5280, which will give you, and all of a sudden we round. Okay, the 3 decimals would be 73.402 miles per hour. And we round it to the nearest mile per hour. So that's how fast the ball is going. That's pretty darn fast, right? So that must come down. It's still coming. That's pretty fast. Or maybe did it go? I guess I didn't figure out when 8 feet. Maybe he caught it as it was going. I don't know. I didn't look at the parabola to see if he caught it when it was going up or when it was coming back down. I don't know. I should just shut up. I'm going to shut up. All right. I think that's it. Yes. Hopefully it all makes sense. They want us to start doing office hours on Monday. If I actually get ahead of the game, I will let you know. But as of right now, I'm planning on doing office hours starting on Monday. If you need me before then, feel free to text me through Remind or message me through Google Classroom, and I'll be happy to. You want to just chat, you need someone to talk to, you want to, because who knows what tomorrow's going to bring. Things are changing every single day, right? So, but we're in this together. We got this. As of right now, College Board is still working out a way for you to still take this AP exam. So we want to keep on going and make sure you're ready for it, right? You don't want to put all of this hard work that you've done all year to let it just go, right? Thinking about all of you, miss you all right? And here's your homework, yes? And definitely let me know if things are feeling overwhelming to you, whatever, okay? I want you to stay, we want to stay on task and stuff, but I also don't want you overwhelmed by any means, right? And I know, yeah. Anyway, okay, I'll see you guys tomorrow, okay? Bye.